Hi, in this video we will explore how to evaluate classification models through performance metrics and how to track experiments. This knowledge is very important. It is the foundation for developing robust machine learning systems. So we're gonna be going through these learning goals, understanding the use of performance metrics for classification, identifying elements in a confusion matrix, exploring the effect of threshold moving on classification metrics, computing accuracy, precision, recall, and the F1 score for classifiers, and checkpointing models with the best performance. So here we're going to start talking about confusion matrices. And we see here the output of the cat classifier. The cat image has a ground truth label of 1.0. It is a cat. And our model predicts y hat 0.95. It is 95% confident that this is a cat. Remember that the model will always output probabilities. So we need to find a threshold in which we binarize the probability. The default behavior that we see in most machine learning libraries is that when the probability is above a 0.5 threshold, we say that this is a positive prediction, that we're predicting that this is a cat. However, there is no rule set in stone saying that we need to use this threshold. If we were to use a much higher threshold, for example, 0.99, we would say that this is not a cat. The prediction from the machine learning model would be a negative then. The confusion matrix is when we count the agreement between the things that we said were positive according to the output of the model and the threshold that we use for binarizing the output and what we have in the ground truth. And we need to be very careful with this because this is a very common point of confusion. People sometimes believe that you can do the encoding the other way around, that you can use the labels of 0 and 1 interchangeably, and this is not the case because these labels are tied to probabilities. So 1 corresponds to a 100% confidence, full probability, full confidence that something is belonging to a class, whereas 0 is the opposite. This comes from probability, and if we want to use functions like the cross-entropy loss to optimize the values of our networks, we have to be very pedantic and very rigorous in the use of this standard. So check out what we have here. This confusion matrix would be this evaluation of what is a true positive, which means when we have agreement between y hat equal 1 and y equal 1. Also, how many true negatives we have, which is the agreement between 0 in the prediction and 0 in the ground truth. And then the other two cases where we're making mistakes, the false negatives. A false negative is when we're saying that the image is not a cat, but is actually a cat. And a false positive is when we're saying that the image is a cat, but is actually not a cat in the ground truth. So this matrix will have the counts for a bunch of test cases. We're going to have 165 test cases, 165 images or cats and non-cats, and we're going to have 50 true positives, 50 real cats being correctly identified, 100 true negatives. This means 100 non-cats saying that they are non-cats, 100 images of dogs, for example, where we label them as non-cats. We're going to have 5 false positives, which means that we're going to have 5 images that are dogs or horses or whatever, mistakenly identified as cats. And then we're going to have 10 false negatives, which are cats that we failed to identify. These images were really cats, but we say that they were not cats. And this is something that we're evaluating in this situation with a threshold for positive that is a default, the one that we see in most machine learning libraries, where we say that if we have a confidence above 0.5, then the image is being labeled as a positive. And if we were to move this threshold, if we were to actually change the value so that it's not 0.5 but it's 0.1 or 0.99, all these counts would be different. This is very important for us to internalize. So let's take a look at what is the effect of moving the threshold in a real practical example of object detection. This slide shows how the threshold choice impacts what are we detecting in the image. If we say that the threshold for positive is above 0.5, the default threshold, you're going to be detecting multiple people in the image with moderate confidence. But check out what happens if I raise a threshold to 0.9. If I raise a threshold, we're going to have fewer detections, and these are highlighted in the image. You see this red circle area where we fail to detect these people that were in the image. So in the remaining detections, we have a higher confidence, but then we miss some things that were supposed to be labeled as belonging to the class. We have some false negatives that appeared on the image simply because we put the threshold at a higher level than the default. So there is a trade-off. When we have a higher threshold for the confidence, we're going to have a classifier that is more precise. It's going to have fewer false positives. But if we lower the threshold, we're going to have better recall, and we're going to be catching more true cases. And it's important for us to remember that there is no perfect threshold. Just using the 0.5 default is not always a good idea. It's often a terrible idea. This depends on the needs of our application. So, for example, if we were to have a security system, we most likely want to have a high threshold in the activation to avoid false alarms. But if we were to be doing medical screening, we actually would like to have a lower threshold so that we don't miss cases, so that we have a higher recall in the cases that we're evaluating. This trade-off is going to lead us to the precision and recall metrics, which we're going to be covering next. And now let's connect our discussion of performance metrics with the cross-entropy loss that we discussed so extensively in the previous video. We were using the cross-entropy loss as a measure of the quality for our predictions. So let's think about what we were doing with the MNIST dataset, and imagine that we have a classifier that does 10 predictions, 7 really confident correct predictions with 0.8 probabilities, 3 uncertain correct predictions with 0.1 probability. And then if we were to look at the values that we have in cross-entropy loss, we're going to get a total loss that is about 0.847. This is a bit hard to interpret. If we were to look at the batch of results, what does that tell us? Well, it's easier to interpret this if we were to just look at the accuracy. It's a simple count. If we were to do this evaluation, that we're getting about, let's say, 7 out of 10 predictions right, and we have an accuracy of 0.7, this is actually more intuitive. And if we were to have a perfect accuracy of 10 out of 10, this is something that is self-explanatory. We have already created a classifier that is doing perfectly. So there is something that is a bit confusing here, and that is that accuracy misses the confidence information that we had in the probabilities, like what we were doing to evaluate cross-entropy loss. The loss function captures more of the prediction quality. However, it is less interpretable. So the trade-off that we have here is that one of the functions is very good for training. Cross-entropy loss is very good for training, but it's not as useful for the evaluation. So that's why we have metrics like accuracy and precision and recall. We actually need to look at both of them to have a full picture about the behavior of our classifier. So this slide also demonstrates another reason why we don't use accuracy to update the model, and that is that it is a step function that is not differentiable. So we cannot really use accuracy to update the weights of the model. We could use cross-entropy, its binary variation, we could use mean square error, absolute error. All of these are functions that have smooth behaviors where we can compute gradients. But the accuracy function, the F1 score, the precision score, they have like this big cliffs where we cannot really compute derivatives. Training is something that needs continuous feedback, so it's something that we cannot really do with the accuracy score. The evaluation really needs some interpretable numbers. That's why we have this 0.7 accuracy or 10 out of 10 accuracy. But training really needs to use a differentiable function like binary cross-entropy or the mean square error. So let's take a look at how we implement multi-class accuracy in PyTorch. So check out what we have here. When we have this multi-class classifier where we just want to get the highest probability as the prediction, we don't really need to work with a threshold. We can simply count the matches in the argmax, where we have the index that has the highest confidence versus the index that we have in the ground truth. We count the matches and then we divide by the total number of samples. The MNIST distribution plot reveals some very important insight, and that is that the dataset is quite balanced. Every single one of the digits is appearing at about the same frequency. So this is something that allows us to get away with using accuracy, but it's something that will be very problematic in datasets where we have a big imbalance between the different objects of interest. Let's take a look at a very important example. Take a look at this image where we have a brain tumor. We are on a case where the tumor is about only 10% of the voxels that we have in the image. A voxel is like a pixel in 3D space, so it's a little cube that corresponds to a little portion of the image. So notice that the majority class that we have in this particular volume is healthy brain. So if we were to create a classifier for tumors, we could say that if we just predict the majority class, if we say that there is no tumor in this particular image, that there is only healthy brain, we will be creating a classifier that has very high accuracy. And this would actually seem pretty good, but it's actually awful. It's not solving the problem that we are trying to solve. We want to detect the tumor, and if we're doing something like radiosurgical planning, we want to get as much of the tumor as possible while sparing the healthy tissue. If we say that, okay, there is no tumor in this particular image, we basically created a useless classifier, but the accuracy is going to appear to be very, very high. In cases like this, we use other metrics that are focused not only on the hits, meaning not only true positives plus true negatives like what we have in accuracy, but they're gonna focus more on the individual classes. So we're going to have a positive class for tumor that is going to be evaluated separately than the positive class for edema and the positive class for healthy brain. And let's understand these two metrics, precision and recall. So notice that the majority class, again, is healthy brain. So if we're going to be using something like precision on the class tumor, we're going to be evaluating the true positives for tumor divided over the true positives of tumor plus the false positives for tumor. So we can only get high precision when we say that the things that we're labeling as tumor are actually tumor. And recall is the number of true positives divided over true positives plus false negatives. So in order for us to get an image that is labeled correctly and in which we're getting all of the tumor, we're going to have to label the pixels that correspond to class tumor in the image. These two metrics, even though they're quite useful, are in contraposition to one another, and we can have a very extreme classifier that has perfect precision but almost no recall, and that is one that picks just a single voxel on the image, says that the voxel corresponds to tumor, and then the classifier is right. That will be something that will have a perfect precision but almost no recall. On the other hand, if we have a classifier that says that everything on the image is tumor and labels every single voxel as tumor, then this is going to have perfect recall but almost no precision. So what we want to do is to have the harmonic mean between these two quantities. The harmonic mean between these two quantities is called the F1 measure. This is a quantity that is only going to be high when both precision and recall are high. And this is something that is very useful and very powerful to use, because then we can get a perfect classifier if we maximize the F1 score. A perfect classifier in the case of the tumor image would be one that captures all of the pixels that are tumor, labels them as tumor, and only those, without labeling any of the edema and any of the healthy brain as tumor. This is something that we use very commonly in imbalance classification sets. And it's also very important to consider this metric when we do the selection of the threshold that we're going to be using for saying that something is a positive or a negative overall for a particular class. Usually, if we maximize the F1 score while selecting the threshold, we're going to get the best performing classifier for our object of interest. So now that we have discussed a lot about metrics, let's see how we save models during training and track their performance. So we usually train models for multiple epochs. We present the data multiple times, and then we keep the models that have best performance. And where do we evaluate best performance? We do this on the validation set. The validation set is the one that we're going to be used to track the value of both the loss and the accuracy in order to determine which is the best model that we have found so far. So when we have a model that has been trained correctly, you're going to see that the training loss is going to go down alongside the validation loss going down. We want to save the model that has the minimum value possible in the validation loss, or the one that has the maximum possible accuracy in the validation accuracy. So this is something that we do in this snippet of PyTorch code. If you take a look at it in detail, you see that we're tracking which is the best accuracy that we have found so far on the validation set. And once we find it, then we call torch.save to save the state dictionary of the model. The state dictionary is going to have all the weights of the model associated to their layers, and it's something that we can save on a PTH file. This is something that we can retrieve later in order to have the best performing model that we have found so far. Something that we're going to see in the practical Jupyter notebook is how we can track these different experiments in our models, like tweaking the parameters, tweaking the hyperparameters, like trying to train them to get as high as accuracy or F1 score as possible, and to benchmark this at the same time that we're saving the models that have the best performance. We're going to be using a platform called Weights and Biases to track our experiments. And this is something that is very valuable for us as practitioners. You're going to be taking a look at the dashboards of Weights and Biases in the practical exercises that we're going to do. So let's recap the takeaways from this lecture. We discussed confusion matrices, which are the basis for all classification metrics. We discussed how the thresholds that we use for positive determine whether we're doing predictions that have certain numbers of true positives, false positives, true negatives, false negatives. And this is something that must match the application needs. We discussed the use case of medical image analysis with brain tumors, and also a brief example about security cameras. So we need to be aware about how this threshold selection is something that is going to be application dependent. So we discussed the use of metrics versus loss functions. We saw how performance metrics help us humans understand the behavior of models better, but that we cannot train models with these metrics. We need differentiable loss functions for training, and cross-entropy loss and mean square error provide us gradients that we can use for this purpose. We see how in the model selection process we should also incorporate appropriate metrics depending on the dataset, and there are different metrics that are appropriate to use according to whether our dataset is balanced or unbalanced. So precision and recall are better metrics for imbalanced datasets, and we saw how we can save models based on the validation performance, and how we can track our experiments systematically using the Weights and Biases platform. We're going to be doing exercises using this in the practical part that I invite you to do through Kaggle.